2006 Grade 11 Hypatia Math Contest. The odd positive integers are arranged in rows in the triangular pattern as shown. What is the 25th odd positive integer? In which row of the pattern will this integer appear? Okay, well, I guess we just have to continue this pattern, and let's see if I can just fill it in right here. So it would be 11, or well, no, not 11, 23, 25 would go here, and then 27, and then 30, 29. Let's just be careful here. And then 31, 33, 35, 37, 39, 41. Okay, I still don't have the 25th number. I gotta keep going here. So 43, 44, 45 I should say, 47, 49, 51, 53, and 55. Now I think at this point I've reached the 25th, because the 25th odd integer would be the number 49, right? And you can count that to verify, and 49 is right here. So that's the 25th positive integer. In terms of what row, well, this was the first row, second row, third row, fourth row, fifth row, sixth row, seventh row. So seventh row. All right, moving right along. What is the 19th integer that appears in the 21st row? 19th integer that appears in the 21st row. Okay, explain how you got your answer. There's several ways of doing this. I think, it all really depends on your comfort level. And I'll just show you the system I used. It's probably a little bit longer than necessary, but I figured, I've got the time. So what I did, I sort of just looked at these numbers that are along that line, I guess. And I noticed that they increased by 2, 4, 6, 8, 10, 12. So you see how they're increasing by a very predictable way. 2, 4, 6, 8, 10, 12, 14, 16, and so on. So then what I did, I just concentrated on this number. And I noticed that if I kind of looked at it, I could get the next number by just adding a very predictable number, right, that I can easily figure out, which is 14 in that case. And when I do add 14, I get up to 57. And then to get the next number, I would add 16. You see what I mean? And then I get up to 73. To the next number, I'd add 18, and that would bring me up to 91. And then you guys get the idea. The next, you'd add 20, and that would bring you up to 111. And then I just kept doing that. And then when I kept doing it, I eventually got to 421. And now let's keep track of the rows, though, because they want you to figure out the 21st row. This 43 was the 7th row, right? 7th row. So this would have been the 8th row, 9th row, 10th row, and so on, right? 11th row. Well, when I got down to 421, this was the 21st row. And that is indeed what we want. But they don't want the first integer that appears in the 21st row. They want a 19th integer. So very similarly how this was the first, this was the second, third, fourth, fifth, sixth, seventh in that row. They want the 19th integer in this row. Okay, so we'd have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21st. Actually, I think I did a couple more than I needed to, so 19. I could probably fit it on one line, just makes it look nicer. Yeah, let me just fit it on one line. So I think that's the 19th one. Let me just check. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Yeah. Okay, let's fill in the blanks here. So we were odd integers, so this is going to be 423, 425, and so on, right? I mean, you guys can do that. And when you get all the way down to here, that number is 4, 57. So, like I said, whatever system you want to use is fine, as long as you arrive at the right answer. The next part. Determine the row and the position in that row where the number 1001 occurs. Explain how you got your answer. Okay. All right, so we are now moving on to the next part. All right, so let's talk about this here. 1001. Okay, so 1001 is the number, but I want to know which odd number is that? Is it the 7th odd number? Is it the 200th odd number, right? So it's a very simple system to figure that out. You just add 1 and divide by 2. And when you do, you get 501. So it's the 501st odd number. You see what I mean? Very similarly, like, for example, if I asked you, in this question, they said, what is the 25th odd number? Well, the 25th odd number was 49. And how you got that is, you just take 49, add 1, and divide by 2, and you get 25th. So 49 is the 25th odd number. Okay, so it's the 501 first odd number. Now, what you have to do is figure out the row and the position in that row. Okay, well, if you go back to this table and take a look at it, you'll notice that this is obviously the first row, right? Row number 1. And there's 1. How many numbers are there so far? Cumulatively, there's 1. This is row number 2. And so far, if you add them all up, we'll have 1, 2, 3 so far. But there's 2 in that row. And cumulatively, well, this would be 1, this would be 3. This row, it's the row number 3, and it has 3 numbers. And cumulatively, if you add up these guys, it would be 6. And then similarly, this is row 4. It has 4 numbers, and cumulatively, you will have so far 10 numbers, right? So it's the same kind of thing that you would have to extrapolate that system to get all the way down to the 501st odd number. So if I asked you, in what row is this 19? Well, the first thing you have to figure out is 19 represents which odd number. Okay, well, that's easy. You just add 1 and divide by 2. So that would be 10. It's the 10th odd number. And then if I asked you in what row and what position, well, here it's all in front of you. But if you wanted to do it mathematically, this is what you would need to do. You would do a simple calculation of adding up the rows, because each row has the same number of numbers, as you can see from this table. So you just go 1 plus 2 plus 3 plus ... n, and that is equal to 10, because you want the 10th number. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And this n represents how many rows. So in this case, you guys know that formula. It's n times n plus 1 divided by 2. That's the formula for the sum of consecutive integers. And in this case, it equals 10. So that means n times n plus 1 is equal to 20. And we can do this in our head. N is equal to 4, because it would be 4 times 5. So that means that in the 4th row, you would find the 10th odd number, which in this case is the number 19. So what we have to do is the exact same thing, but this time we have to do it for the 501st odd number. So the same thing, 1 plus 2 plus 3 plus ... plus n, this time equals 501. And then again, that formula is n times n plus 1 divided by 2 is 501. And now we have n times n plus 1 is equal to 1002. Now, you can do a quadratic, but I just do an estimation. And what I do is say n times n plus 1 is very similar to like n times n, right? So if you have n times n, it's really n squared. So just take the square root of that to get a very approximate value of n. And when I did, I got n equal to approximately, I think it was like 31.6 or something. So that means I'm going to try n equals 32. So let's see what happens. And when I tried n equals 32, I basically, when I put it in this formula right here, I got 32 times 33 divided by 2, which is 528. So that means the 528th odd number is in the 32nd row. So we are really just concentrating on this part of the triangular pattern, right? The very last number. So the very last number in the 32nd row would be the 528, the 528th odd number. So the 501st odd number would be somewhere along the line. It would be somewhere behind it, somewhere before it, I should say. Got it? So basically, if you had a row, let's just pull this up now. You're going to have the very last number will be the 528th odd number, right? Which is what in terms of a number? The 528th odd number, I believe, is 1055. Yeah, because it would be 1055 plus 1 divided by 2. So then somewhere, dot, 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 in this row is our number, which I believe was 1001, which is the 501st odd number. And this was row number 32, right? Row 32. Well, how many numbers are in row 32? 32, correct? Just like before. Row number 1 has one number. Row number 2 has two numbers. So row number 32 would have 32 numbers. So we start off with some number, and then eventually you get down to the 32nd number. So this was the 528th. So let's think about this for a second. So 1 through 28 is 28 numbers, and I need 4 more, right? So I would need a 500, a 499, a 498, and a 497. So in this row, this would be the first, second, third, fourth, and then this would be the 5th. So it would be the 5th number in the 32nd row. And that completes this question. Number 2, in the diagram, triangle ABE, BCE, and CDE are all right angled, with angle AEB, angle BEC, and angle CED equal to 60. AE is 24. Determine the length of CE. Well, the famous 30, 60, 90 triangle will be utilized throughout this question. Let's say this is 30 degrees and 60 degrees. So hopefully by grade 11, you should know that the ratio of the sides of any 30, 60, 90 triangle are 2, 1, and root 3. So since we have a whole bunch of these, we just have to use that property. So let's see here. Let's see if I can label this properly. This is 60 degrees, so therefore this would be 30 degrees. This is 60 degrees again, so this is 30. And then this is 60 in here, and therefore this is going to be 30. Okay, so in this first triangle, we can figure out the values pretty easily. They gave us the AE is 24, right? So this is 24. And this is the ratio 2, 1, and root 3. So that means that BE would be 12, right? Based on the ratios alone. Okay, that's pretty easy. Now we have to calculate CE. So CE, let me just draw this over here so I don't make it confusing. So this is the BEC triangle, and the ratios of this one are 2, 1, and root 3. But we already figured out that BE is 12. So that means CE would be 6. And that's it. So CE is 6. All right, part B. Determine the perimeter of quadrilateral ABCD. All right. So I guess we have to figure out all of these lines. I think so far we would be able to get all of these with just this 30, 60, 90 triangle relationship. So that means if this is 12, this would be 12 root 3, this AB. If this is 6, BC would be 6 root 3. And then let me just draw that tiny triangle over here just to avoid making the diagram messy. C, E, and D, right? So CE was what? 6? And then what was the ratio again? This is 30 degrees, this is 60 degrees. So the ratio would be 2, 1, and root 3. So that means ED would be 3, and then CD would be 3 root 3. All right, great. So let's label this now. BC, I think, was 6 root 3. CD I got as 3 root 3. ED I got as 3. And I think that's it. So perimeter was going to be 12 root 3 plus 6 root 3 plus 3 root 3 plus 3 plus 24. And I believe that is going to be equal to 21 root 3 plus 27. All right, that takes care of B. Part C, determine the area of quadrilateral ABCD. Okay, so basically the area would be 3 triangles all added up together. So we'd have 1/2 base times height. Essentially 3 times probably. Yeah, because 3 triangles. So 1/2 base times height 3 times. So 1/2 base times height plus 1/2 base times height plus 1/2 base times height. And let's fill in the bases and the heights. So the first triangle, the base is 12, the height is 12 root 3. The next triangle, where is it? Over here. The base is 6, and the height is 6 root 3. And then the small triangle, the base is 3, and the height is 3 root 3. Okay, so this looks to me like 144 root 3 plus 36 root 3 plus 9 root 3. And of course, it was all over 2. So that's going to be, what is that? 189. 189 root 3 all over 2. And that completes number 2. A line L passes through the points B, 7, -1, and C, -1, 7. Determine the equation of this line. Okay, well, done this a million times. Y equals mx plus b, with m as the slope. M in this case is rise over run, which is the difference of the y values. So in this case, -1 minus 7 over the difference of the x values, 7 minus -1. So that looks to me like -8 over 8, and that's -1. So that's the slope. So therefore, the equation is y is equal to -1 times x plus b. Now, of course, we got to figure out b. You can do that by substituting any of these points. Let's just sub in, well, it doesn't really matter. Put in the b, and we get -1 is equal to -1 times 7 plus b. And therefore, b would be 6. And therefore, our equation is y is equal to -x plus 6. Great. Now determine the coordinates of the point P on the line L so that P is equidistant from points A and O. All right, so I will attempt to draw this to make this come to life. So let's see here. 7 and -1, so somewhere here. And then -1 and 7, so somewhere here. Okay, I gotta connect these, so something like that, right? Okay, that's my L, so just put L up here, and that equation is y is equal to -x plus 6. And then they're saying that you have A and O, so O is the origin, so that's easy. Let's just put a little dot there to represent O, this guy right there, and then A is 10, -10, so 10 and -10. Okay, so A is going to be somewhere down here. Let me think about this. Somewhere here, right? Yeah, 10, -10. Okay, and they're saying that there's some point P on that line so that it's equidistant from those two. All right, so I don't know where P is, so let me just guess and say it's I don't know, somewhere here, let's say. So that means if you were going to draw a line from P to O, it would be the same length as from P to A. Looks pretty decent. Okay, let's go with this then. All right, so let's start labeling this. P is on that line, so that means all coordinates would be of the form x and minus x plus 6. All right, so let's just take what they've given us, which is P. And moving on, this would basically be following their PA is equal to PO requirement. So here we go. So we're going to use the distance formula. So P to A would basically be x minus 10 all squared plus y, y in this case is minus x plus 6 minus 10 all squared. And the distance is calculated by taking the square root. So that's PA. And we want that equal to PO. And PO is just simply x minus 0 squared plus this minus x plus 6 minus 0 all squared under the square root sign. Okay, so that's all there is there. So now we have to simplify this. The first thing I'm going to do is square both sides. And then I'm going to expand this a little bit. So this will become, let's see here, x squared minus 20x plus 100. And when you expand this guy here, that's x minus x plus 16. So it's going to be x squared plus minus 32x, I should say. And then 16 squared is 256. Okay, and then this side is relatively straightforward. When you square both sides, the radical sign disappears and you just have x squared plus x squared minus 12x plus 36. Okay, great. So let's simplify this a bit. Let's put this all on one side if we can. I think the x squareds all go, so that's good. And then we'll have a minus 52. I think I forgot an x there. And then if you add 12x will be 40. Yeah, minus 40x on one side. And on the other side it'll be 356 minus 36, so 320. And therefore x would be 8. Okay, great. So then to get the y value, we would just substitute it back into this equation. So that would mean minus 8 plus 6 minus 2. So the coordinates of P are 8 and minus 2. Part C. Determine the coordinates of all points of Q so that so that angle OQA is 90. OQA is 90. Okay. So let's see now. So let me draw this again. I'll just do it on the same graph. OQA is 90. So maybe let's just, I have no idea, but let's just approximate. Does that look like 90 degrees to you? Yeah. So let's just say that's one possible Q. Yes, because it's got to go through A, right? So, okay. Now let's see, how are we going to do this one? The first thing that I thought of that kind of makes me, look at this question from the perspective of the triangle, which would be Pythagoras, but I think that might be a little too complicated. I think we'll probably just look with slopes. I think that would be better. If this is a right angle, then that means the slope of this line and the slope of this line will be negative reciprocals. So two slopes that are perpendicular, that's the sign for perpendicular, have the property that the slopes are negative reciprocals. Slopes are negative reciprocals. And what that means, I mean, you guys know, but I'll just mention it. For example, if one slope is, let's say, a half, the other one will be the negative reciprocal. So the reciprocal is 2 and then negative. Or another way to do it, if this is m1 and this is m2, m1 times m2 is equal to negative 1. And that's also a property of negative reciprocals. So I think that's what I'm going to do in this question. It's probably better than Pythagoras, like, you know what I mean? Like using that and then calculate the distance here and distance here. And I think that would be a little too complicated. Okay, so here we go. QO, the slope would be, well, what is Q? Q is on that line, right? So again, it's going to have the form x and minus x plus 6 in terms of its coordinates. So the slope would be minus x plus 6 minus 0, and then x minus 0. So that's just minus x plus 6 over x. And then QA, that, okay, we got to take into consideration that point. So that's going to be minus x plus 6 minus 10. And then x minus, wait, hold on a second. I think this is plus 10, right? Because it's minus 10, and this is minus 10. Okay, I got to make sure I don't make any mistakes here. So this is going to be minus x plus 16 and x minus 10. Okay, so these are the two slopes, and when you multiply them, they got to equal negative 1, because that's the property of negative reciprocals. So that means that x plus 6 over x times this minus x plus 16 over x minus 10 is equal to negative 1. All right, that doesn't sound so bad. So let's do this now. Multiply these two and these two. Okay, so the top would become, oh boy, x squared minus 16x minus 6x plus 6 times 16, which is, I believe, 96. And then this one on the bottom is just x squared minus 10x. So I guess on the top we'll have x squared minus 22x, or 22? Yeah, 22x, and then plus 96. And on this side is just 10x minus x squared. Okay, so if you put everything on one side, it'll be 2x squared minus 32x plus 96 is equal to 0. And then divide through by 2, and you'll get x squared minus 16. X squared minus 16 x plus 48 is equal to 0. And I think this factors very nicely. X, what is it, 12 and 4? Yeah, 12 and 4, and then minus, right? So that means x is equal to either 12 or 4. And then the corresponding y values, you just plug it into that. Y is equal to minus x plus 6 line equation. So that would give you minus 6 and 2. So the points Q would be either 12 minus 6 or 4, 2. Yeah, okay, great. That completes that question. The abundancy index I at n of a positive integer n is I at n is symbol n over n, where symbol n is the sum of all the positive divisors of n, including 1 in itself. For example, I at 12 is 1 plus 2 plus 3 plus 4 plus 5, plus 4, 6 plus 12 over 12 is 7 over 3. Prove that I at p is less than or equal to 3 over 2 for every prime p. All right, great. So let's see what we can do here. Let's just give an example first kind of explain what is going on. So let's say we have a number n, and let's just give a simple example. Let's give 10. And then let's talk about what are the positive divisors. Positive divisors are 10 are 1, 2, 5, and 10, I believe, right? I think those are the only positive divisors of 10. So therefore, by definition, this I of n, in this case I of 10, would be the sum of those guys, so 1 plus 2 plus 5 plus 10, all over n, which is 10. So in this case, this looks like what? 18 over 10? Yeah, which in lowest terms is 9 over 5. And that's essentially what they did with 12. First, they listed the positive divisors. They put it over 12, and then they added it all up, and they obviously reduced it to lowest terms to get a 7 over 3. Okay, so now that you understand, let's talk about part A, which is prove that I at P is less than or equal to 3 over 2 for every prime. If a number is a prime, that means its divisors are very limited. The only divisors are 1 and itself. That's the definition of a prime number. So therefore, I at P would be pretty straightforward. The sum of the divisors would be just 1 plus P, and then, of course, over P. And if you break this up, this is 1 over P plus P over P, which is essentially 1 over P plus 1. And because P is a prime number, P is always going to be greater than or equal to 2, right? Because prime numbers are 2, 3, 5, and 7, and so on. So this means that 1 over P is always going to be less than or equal to 1 over 2, correct? Because if P was 3, it would be 1 over 3, which is less than a half. P was 5, it would be 1 over 5, which is less than a half. So therefore, this is always going to be less than or equal to 1 over 2 plus 1, which is essentially the same as 3 over 2. And I think that is it. You basically have shown that I at P is less than or equal to 3 over 2 for any positive, for every prime number, basically. And I think that's it. I don't know what else you would do. I mean, you can add some more sentences, or you can give some examples when P is equal to 3, P is equal to 5, and sort of explain it a little bit further if you'd like, but I think that should be sufficient. Okay, part B, let's go here. For every odd prime number P for all positive integers K, prove that P at K is less than 2. All right. Okay, so this is a little bit different, and I think I'm going to need a little bit more space. So we are trying to prove that, oh, this time it's odd. Okay, so odd primes, well, every prime number is odd, right, except 2. So basically every prime number, so I guess the only criteria is that P cannot equal 2, right, because 2 is the only even prime number. And then they want you to prove that I of P at K is less than 2. All right. Okay, so we have to use a full screen here. All right, let's talk about this first before I jump into a proof, because the proof might be a little too abstract if I don't talk about it first. All right, so basically, let's just use some numbers. Let's say P is 3. Okay, and let's just make K equal to 2. That means we have I of 3 to the power of 2. And how do you calculate this I? Well, this is basically I at 9, right? You take the divisors of 9, which are 1, 3, and 9, and then you'd add them, and then you divide by that 9. So in this case, this looks like 14 over 9, or 13 over 9, sorry. Okay. So, and that is indeed less than 2. Okay, great. We haven't proven anything, but we have shown that for at least one example, it's true. Let's try another one. Let's try P equals 3, but this time K equals 3. Now we have I 3 to the power of 3, which is essentially I of 27. Yeah, I at 27. So same thing, we take the divisors of 27, which are 1, 3, 9, and 27, I believe. And then we add them all up, and then you divide by 27. And that would be 40. 40 over 27, which again is less than 2. And that doesn't prove this, but it does give another example. So I just wanted to show those examples to kind of talk about what it is that they're asking. Okay, now let's talk about this in general. So in general, how would you approach this? Well, it seems to me from these examples that any I of p at k would be basically 1 plus p to the power of 1 plus p to the power of 2 plus dot 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 all the way up to p to the power of k. And if you notice, especially in this one, you can see it's 1 plus 3 to the power of 1, 3 to the power of 2, and 3 to the power of 3. And of course, you divide by p to the power of k. And that's just the basic definition of this function, I at something. Okay, so I think we got something here. Perhaps. Yeah. All right. Okay, so let's see what we get. I think if we put it over each one, it might be a little bit simpler. So for example, this 1 over p at k, if you break it up, plus p over p at k, so it'd be 1 over p of k minus 1 plus 1 over p of k minus 2, like that, and then dot dot dot, and eventually you'd get to just 1 p over k plus over p over k. At this point, this is something that I can work with because this is a geometric series. Yeah, and the good news is that for geometric series, they have a special formula. And this is not infinite, because the infinite formula was, I think, a over 1 minus r, I think. But this is not infinite. So this finite series has the following formula, and some of you may remember this. It's a times 1 minus r to the power of n, all over 1 minus r. So in this case, a is the first term, r is the common ratio, and n is the number of terms, right? Yeah. So how many terms do we have? We'd have 1, 2, all the way to k, but then we have this extra 1. So we have k plus 1 terms. So the n is k plus 1. The a is the first term. But you got to be careful here. I'm actually going to write this in reverse order. So 1 plus dot 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 plus 1 over pk minus 2 plus 1 over pk minus 1 plus 1 over p to the power of k. If I do it that way, then I can list the first term as 1 right here. I think it just makes it a little bit easier. And then what else do I need? Oh, I need r. Okay, so what's r? R is the common ratio, right? So in this case, the common ratio would be, well, let's just, usually it's just the last term divided by the first term. No, sorry. The last term divided by the second last term. So this is the common ratio, which is p to the k minus 1 over p to the k, which is 1 over p. Yeah, 1 over p. Okay, so r is 1 over p. Okay, I can do this as this. I can add this up, basically, the sum. So this a is 1. I have 1 minus 1 over p to the n, which is k plus 1, and then 1 minus 1 over p. All right. Let's work with this. I think this should give us what we need, which is we're trying to prove it's going to be less than 2. All right, so let's do this carefully now. We've got, well, 1. Let's break it up. This 1 with 1 over 1 minus p, and then minus 1 over p to the power of k plus 1 over 1 minus 1 over p. Yeah. I think that would be helpful. And then I noticed that you can say that since this minus this is going to be less than or equal to 1 over 1 minus 1 over p, right? Because, for example, if this thing here was whatever, let's say it was 5, and this was, let's say, 2, then it's safe to say that since you're always subtracting something, it's going to be less than that original thing. So this is a very important point, a conclusion I can make. Now I just keep going here. This, if you simplify it, would be 1 over p minus 1 over p, which is essentially the same as p over p minus 1, which is, let's see here, yeah, p over p minus 1. And then if I do a little bit of fancy algebra like that, then I can break this up into p minus 1 over p minus 1 plus 1 over p minus 1, which is essentially 1 plus 1 over p minus 1. And 1 over this guy right here, since p is a prime number that is odd, it's going to be either 3, 5, and so on, then that we can clearly say that that's going to be less than or equal to 1 plus a half. Because if it's 3, it would be 1 over 3 minus 1, which is 2. If it's 5, it would be 1 over 5 minus 1, which is 4. So this is another key statement that is valid, and that's essentially equal to 3 over 2, which is less than 2. Yeah, so we have proven that it's less than 2, and we started basically with I of pk. And I think that's what they wanted, right? There you go. So a little big long song and dance, but we got the final conclusion. Part C. If p and q are different prime numbers, determine I at p squared, I at q, I at p squared times q, and prove that I at p squared times I at q is equal to I at p squared times q. Okay, so let's just figure them out individually. I at p squared, that would basically be 1 plus p squared all over p squared. Right? Basically according to the definition that they gave us in the question. I at q, well, q is a prime, so that's just 1 plus q over q. And then this I at p squared, q, that's going to be, let's see here, how many, this is like 1, so there's going to be 6 divisors, 1 p squared, pq, q, and then of course the entire thing with this p squared q, and of course we're going to divide by p squared q. Okay, so that's this part of the question. Now we have to prove this part, which is if you multiply this by this, you get this. Okay, so prove that I of p squared times I times q is equal to I of p squared q, right? Okay, so let's do the left side equals right side. So left side, I've already figured these out, so I'll just sub them in. 1p plus p squared over p squared. And then this guy, 1 plus q over q. And let's expand this. When you expand it, you get, let's see here, 1 plus q plus pq plus p squared plus p squared q all over p squared q. And that looks to me like essentially this, which is I p squared q. So this is pretty much all you need to do to solve or prove what they want in part C. Okay, the last one. Determine with justification the smallest odd positive integer n such that I at n is greater than 2. All right. So the good news with this one is that parts A, B, and C and all sort of help us to try to solve this part. Otherwise, if you had never seen parts A, B, and C and never worked them out, it would be very difficult. So let's just recap a little bit. Recall, if you remember, that in part B of this question, we had shown that I of n is less than 2 when n is prime. Right? Let's see here. Where was it? Yeah. For in particular, any odd prime. Yeah. But in this case, they want you to prove that it's greater than 2. Okay. But we want I of n to be greater than 2. So that basically means that we will need a bigger number. We will need more than just 1 prime. So that means that n perhaps is 2 primes multiplied together. So like p and q, or both p and q are prime. Let's see. I mean, I'm not sure, but let's see what happens. If that is the case, then let's say we try something like, let's just do experiment. We try p equals 3 and q equals 5. These are the 2 smallest primes, right, that are odd. And therefore, n would be equal to 3 times 5. But then, of course, they're going to have some component, exponents, I should say, a and b. I don't know what they are, but whatever they are. And therefore, I of n, in this case, would be I of 3a times 5 to the power of b. And we can split this up, right? From, remember, part C, we were able to conclude that this can be split up. The properties allow us to split them up like that. And also, if you remember, we recall that we already proved that anytime you have I to the pk, it's less than p over p minus 1. Right? You guys remember that? That was from a previous part also. So these two guys basically would mean less than p over p minus 1. So 3 over 2 times 5 over 4. And that is equal to 15 over 8, which is less than 2. So again, we've run into this problem that we got, again, a less than 2 situation, but we want greater than 2. But we want I of n to be greater than 2. Okay, so from this small example, I'm concluding that even when you use 2 primes, it doesn't give us the greater than 2. So that makes me think, okay, then n has to be 3 primes. So n's got to be, let's say, perhaps 3 primes. So p times q times k or whatever, where p, q, and k are all primes. And they also want us to use the smallest possible. So let's use the smallest possible, which would be the smallest possible odd prime numbers, which are 3, 5, and 7. So let's say n would be 3 times 5 times 7. And of course, we've got to have these exponents because we don't know what the exponents are. And let's work with this. And let's see if we indeed get an I of n greater than 2. All right, so let's see. Let's make a little table. We got A, B, and C. We got n. Then we have I at n. And then let's see if it's greater than, we want it to be greater than 2, right? And let's put a question mark, yes or no. All right. Hopefully I don't have to go through too many. And let's see. So let's start off with the smallest because we're concentrating on the smallest, 1, 1, 1. If that's the case, n would be 3 to the power of 1 times 5 to the power of 1 times 7 to the power of 1, which is 105. And the I, therefore, of 105 is I of 3 times 5 times 7, which is the I of 3 times the I of 5 times I at 7. And using the property from before, this is 4 over 3 times 5 over 4 times 8 over 7, which is 64 over 35. Now, that is unfortunately less than 2, so it doesn't satisfy that property. All right, no problem. Let's just keep going. Let's try the next 1. I'm going to concentrate on making this as small as possible. So 2, 2, 1, 1. And this time n would therefore be 3 to the power of 2 times 5 to the power of 1, 7 to the power of 1, which is 315. And the same story, I of 315 would be I of 3 to the power of 2 times 5 times 7, which is I at 3 to the power of 2 times I of 5 times the I of 7. And this, you can easily calculate this. This would be 13 over 9. I think we even did this one before. This is 5 over 4. This is this is 6 over 5. I think I made a mistake up here somewhere. Yeah, this should have been 6 over 5. Yeah, sorry about that. So yeah, because 24, 48, and then we had to reduce it to lowest terms, right? Yeah. 4 times 8 is 30. Yeah. Okay, sorry about that. So this is not 5 over 4. This is 6 over 5. Just got to make sure I don't make any mistakes. And this is 8 over 7. And when you multiply all these, it's 208 over 105. And that is still less than 2. Okay, so we still haven't satisfied that. All right, let's keep going. Hopefully we'll get it sooner rather than later. Let's try 3. This would be 3 to the power of 3, 5 to the power of 1, 7 to the power of 1, which is 945. And therefore this would be the I of 945, which is I of 3 to the power of 3, I to the power of 5, and I to the power of 7. Or not power, but it's a function. So this is going to be 40 over 27, which I believe we had done earlier in the question. This is 6 over 5, and this is 8 over 7. And this is equal to 128 over 63. And this is indeed finally greater than 2. So we got it. And that is for 945, right? And then all other n's would be bigger than 945, for which this property holds true. So what was the smallest odd positive integer n? So that was 945. And that completes this question.